Okay, so let me first find where we stopped last time. We did basically these are the topics of the first day, and we definitely did the first two, the representation of the features. So as I browse, we spoke about the notation, we spoke about the way it's represented as instructions or a piano roll, which is a graphical representation of the same thing, how we need an instrument to produce it, how this can be automated as a performance machine, the structure of MIDI, the musical instrument digital interface, how it translates to sound through an instrument that is being played, what is a waveform, how waveforms can become pretty complex, and we can basically either combine them together or break them into the constituent basic waveforms, which are the sine waves, and that will be our Fourier transform later on. But if we apply this Fourier transform technique to an existing sound, we can actually break it into the constituent frequencies. So this is kind of why we want to use this analysis, because if you want to relate the notation to the sound, it's very hard to know what's going on in the waveform, but we can still get a better glimpse into the sound if we actually look at the frequencies as they change over time. So we kind of like looked into these three main representations. Actually, the data will be stored either as a piano roll MIDI file or as a recording wave file MP3, and then we will often analyze this as a frequency. And we spoke about the difference between what the notes represent and what the sound is comprised of in terms of the frequencies over time. And then, this sort of an idea that you can actually paint frequencies with the sound, but the typical sound picture is this sort of lines or squares over time because of the nature of the musical sounds, and this is really a noise signal that is designed to paint a picture. Speaking about features and structures, we talked a little bit more about the sheet music representation, how it can differ. I mean, the same music can be actually played by multiple instruments. So you represent them in a much more elaborate ways, and you can synthesize this by multiple instruments. In cases of more of improvised music or jazz, very often we just give some information in one form and the other will be recorded as chords. And we pretty much stopped here, where I suggested some software which are not really part of the class, but these are kind of free online tools that once you have them, you basically have your own musical little studio on your laptop, where with LMMS you can record, and it's kind of a Fruity Loops free version. Audacity is an audio editor, and MuseScore is a notation software. We might want to use MuseScore in some of the exercises, or you can use LMMS, because if we want to handle MIDI files, you probably need either the LMMS or MuseScore to look into them. And for audio, you have Audacity. Well, audio you often can play just straight off your desktop, but MIDI is not anymore. I mean, it used to be that MIDI players would be part of the operating system. You would click and play something in QuickTime. I think most of the computers now do not allow you just to have a preview or playback a MIDI file. You do need the software to run them. Okay, so this is where we stopped last time. And I want to talk a little bit more about the audio features, because we spoke a lot about the symbolic representation. So we kind of try to relate them. And a lot of this is kind of a review. So I don't know if there will be a lot of new material right now, but just to make sure we all have the same terminology. So audio representation, one concept that is common in music, so just really just the definition of the word timbre. Timbre is a word that represents the quality of the musical sound. Some people call it sound color, but the idea is that it's something about the sound that allows you to recognize or distinguishes different types of sound production, such as voices or instruments. So the idea is, if you have the same note played the same dynamics, basically the same volume, same loudness, um, and same duration, but by two different instruments, you would still hear them different. So, if when we speak about notes, we usually talk about the name of the note or the pitch, C, whatever, C3, C4, you have a duration, that's everything we mentioned before. Timbre is often not included as explicitly in symbolic representation, but it's present in the recording. So you pretty much can see from what we discussed before that timbre is basically the spectral shape. It's the way that the partials or the sinusoids combine together to create the actual sound. Of course, it has much more than just sinusoids. It has aspects of noise. It has maybe even aspects of some reverb that goes on, because I'm not speaking about room reverb, but the instrument itself has a resonating box if it's a guitar or violin or piano. So it's not just the pure tones. It's the whole collection of frequencies that create that timbre. But this is kind of the missing link between the audio recording and the symbolic representation. So this kind of a missing link is the sound color or sound timbre or tone quality. And as we said, it's the energy distribution of the harmonics, but it's even more than that. It's the relations between the actual sinusoids. So it will have also, a true representation of timbre would be having the full information about it. As a template, we really often disregard phases, and we'll talk about what the phases are, and just look at the amplitudes or the energy of the partials or the harmonics. So pitch, we define pitch. So this is more of a summary. It's the relation between the key that you press and the frequency, the physical frequencies that you perceive. So the idea is that pitch is more. So there's the key. You press the key produces a frequency, but you hear that frequency. So pitch, in some sense, is a perceptual aspect. Okay. So it's the property that correlates to the perceived frequency. So you perceive basically a height of that note, and it's often related to the fundamental frequency. It's almost equal to the fundamental frequency, but you can have all kinds of acoustic, I wouldn't say paradoxes, but acoustic special ways that you can create a perception of pitch without having the fundamental frequency. We'll skip that, but it's the relation between the partials and the lowest partial eventually comprise something that you perceive simply as a pitch. It's a note that has a periodic component, and you can whistle it or you can sing it. So, for example, A4 is conventionally, that's a convention, tuned to be 440 hertz. That's an orchestral tuning. Some orchestras tune it slightly different, but we will use this as our standard tuning reference. And then when we have somehow little changes in frequency, we could still perceive it's pretty robust to small perturbations. So if you have different harmonics, you might have little vibrato, or which is like a change or modulation on that frequency. You would still have pretty solid perception what note is being played. Another thing is that the way we perceive pitch, it's not linear in frequency. So we will come back to this when we talk about Mel-frequency representation. The analysis we did so far, in all the graphs, the frequencies were going linearly, but the way we actually perceive it is that our sensitivity is doubling with frequencies, or not doubling, it's going logarithmic, and the invariance, where we're doubling the frequency, is called an octave. So really just the terminology for those who are not familiar with the musical theory or the basic acoustics of music. Why doubling of frequency is called octave? Octave is 8. And this is just because on the keyboard, if you go 8 notes on the white keys, you end up, let's say, starting in C3, you'll end up in C4. So it's kind of a strange blunder of terminology, because what has, in Latin 8 to do with doubling, and this is just because this is how the keyboard is organized, and we even skip the black notes. So just remember that octave is doubling of frequency. Really no other connection between these two meanings of the word, except for the fact that it's mapped through the white keys on the keyboard. One specific thing to kind of keep in mind is that once we decide which frequencies we choose, or how we tune our notes to hertz. So hertz is the physical thing. The keys are tuned and we perceive them as pitch, but we have discrete pitches. We have continuous hertz. I mean, the physical frequencies can be anything, but notes on the keyboard are discrete. So people have been talking about how do you basically tune. So if you think about the piano, if you come with a tuning, you come with a fork and the tuning. I don't know how to call it. It's not a screwdriver, but something that you basically can increase and decrease the tension on the strings. It changes their tuning. So there were a lot of arguments about how you actually select the frequencies of these 12 notes that comprise an octave. So the black and white keys, we have 12 total, and then we need to choose the frequencies. So for our purposes, we just need to know that it kind of became, in Western music, the standard way of tuning is so-called equal temperament, where equal means that you take your octave, and because it's logarithmically spaced, you divide this in equal steps. So the equation, let me see if I make the recording actually have the bar blocking my view. So if we have now the relations of, in Western music, we divide this into 12 equally spaced frequencies, or we call 12-tone equal tempered scale. So we have pitches, okay, that correspond to piano keys. And then, so this would be the pitch that we perceive or we notate. This is the piano key, okay? And then we have to tune them to some kind of a standard point of reference. So we choose the A4, which is key number 69 in MIDI, into 440 hertz. Again, bunch of conventions, right? But so just what this data means, right? So the 12-tone equal tempered scale, or the equal tuning, is done by this equation. Now, it might look a little strange, okay, but it's really very simple. What it tells you is, if we take the 69, okay, as our 440, right? So if we put here 69, this is 0, what we get is basically that the pitch in hertz of note number 69 is 440, right? Now, if we go 12 steps up, okay, so, or let's go 12 steps, let's go up just because it's easier, but you can go down as well. So 69 plus 12, right, plus 10 is and what is it, like 69 plus 12, we will get 79, 80, 81, right? So if we put here 81, right, minus 69, we'll have 12, right? So 12 divided by 12 is 1. So basically we double the frequency, right? Same thing if you go 12 steps down, and if we are 69 minus 12, right? So we'll be in 57. So 57 minus 69 will be minus 12. So this will be minus 1. This will be half. So you get to 220. So at least, it's evident that every 12 steps we either double or we halve or divide by 2 the frequency. And every step in between, it's basically moving by the 12's root of 2. So one step up or one step down on a keyboard is translated to physical frequencies that move by the 12, so it's 2 to the power of 1/12. If you open a calculator and compute that number, it's about 6%. It's 5.9% change in frequency. So by moving up or down on the keyboard, you basically change. If you decided what is your reference tuning, and in this case was 440, moving up and down will basically multiply or divide this frequency by 1.0059. And one way to think about this is basically, if you think about a little bit less than, it's about 5.9% interest rate per month because you have 12, right? So if that's the rate you pay, after 1 year you double your debt, right? So this is basically kind of a compound interest if you want. You start from a note, you go up, you add 6%, you keep on adding up, you end up after 12 steps, your frequency is doubled, or you go down. So sound itself, the audio itself, could be analyzed as superposition of sinusoidals, and this is the Fourier analysis that will go in more in detail later. Now, complex musical notes or tones have a lot of these sinusoids, so when realizing musical notes on an instrument, one obtains a complex superposition of pure tones and other noise-like components, and we didn't talk about how they change over time. The notion of harmonics, we said these are specific relations between these sinusoidals where they're integer multiples of fundamental frequencies. So if you go back to the slides, I just don't want to move back and forth, kind of trying to be a little short on time and effective. But if you look some slides up, you will see that the spacing between the lines in the frequency analysis is equal. So we have this kind of a comb or a grid that is created. So if you play a note, an A, at 440 hertz, most likely, unless it's a pure sinusoid, most likely you'll have another sinusoidal components that we'll call first overtone will be at a double of that frequency, and then the next overtone, or the third partial, will be 3 times 440, which is 1320 hertz. Again, plus minus, these frequencies have little variations, vibrations. They're not pure frequencies, but I think it gives a good starting point to understand how frequencies, pitches, timbre are related. So kind of to summarize, what we have is this kind of duality, or it's not exactly duality because there is much more information in the waveform, but it's hard to go back to the notation. So if this is our notation, this is our symbolic representation, and we record it. Here we have actually multiple notes playing together. In this case, the fifth of Beethoven, they're all octave related. So they're all doublings of frequencies, but still you have something going here, da 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 da, and then you have da 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 da. And if we take, let's say, some small window, we cut a portion of this sound, we look at this, we zoom in, you see that this is a periodic waveform. It's not exactly periodic, right? It kind of keeps changing in amplitude, and even the waveform slightly changes. But as a first approximation, just to understand the relations between frequencies and waveforms, is, as we said, this is a note. This note, if you look it up on music notation or on the keyboard, it's D second octave, the lowest note, which is about 73.4 hertz if we tuned it according to the standard tuning. So this note is supposed to be a wave that has 73 repetitions a second. So what is hertz? Hertz is a unit of, and I guess everybody has to take some physics, so hopefully you have encountered this term. Hertz is 1/2, which basically tells you how many repetitions a wave or a periodic element, periodic element, not in the physics sense, a periodic wave has in a second. So a wave that has 73.4 hertz frequency means that these waves would repeat 73.4 times a second. Here we have a window which is 500 milliseconds, from 7.3 seconds to 7.8 seconds. And if we calculate the repetitions, right, these red dots on the top of the waveform, we have 37 periods, which is approximately half, because it's half a second. So we have approximately 73 hertz or 74 hertz wave here. And this is really the correspondence, right? This is the pitch. Now, what happened to all the other pitches? Well, because they're all doubles, the lowest frequency will be still this one. And because these add up as multiples, what we'll see there will be, I mean, a lot of this will be also kind of added together into the shape of that waveform. Do we perceive this as three separate notes if they're all octave related? Or this just creates one immense D2 note with some of these higher doublings just emphasized? That's a very interesting question, basically, how these things blend into perception of single pitch. Of course, if they're different notes, we will hear them as different notes, but if it's the same note played octaves up and up and up, we will have many times the difficulty separating them and saying these are actually three notes, because they blend so perfectly together. If they're played on different instruments, yes, we'll recognize the different timbres. If it's the same instrument and they have, they play together on the same moment very smoothly, we might basically not know that there are basically multiple notes being played together. So this is kind of the summary of the relation between audio and symbolic representation and the physical meaning of these units. So to summarize the waveform, if it's a pure tone, you have a sinusoidal waveform, which doesn't have other harmonics, but you can have more partials if this is periodic, nicely repeating sound, but the shape of that waveform is not a pure sinusoid. And in some sense, the sine wave is our basic, the simplest acoustic waveform, or we can call it the prototype of an acoustic realization of a musical note. We said the parameters, you have a period, which is time between these peaks or valleys, or that's when the waveform repeats itself. We say time between successive high pressure points. Frequency is 1 over this. It's 1 over time. And amplitude will be basically how high or how low. Let me quickly mute. I think just a second. Yeah, somebody had a microphone open. Sorry about that. Okay, so a little bit more into content features, and this might be slightly looking more elaborate, just because so much information about the details of tuning and stuff like that. But I would, once we start talking about having structures like chords, like melodies, we go one level higher in complexity of the signal, and we have to deal with simultaneous notes or patterns of notes, combinations of notes. And one very powerful feature that we will be using, and many other applications take advantage of, is called the chromogram. So what is a chromogram? It's really specific to music. Chromograms are not common in speech or in other signal analysis, and the chromogram is actually designed to take an audio signal, take the frequency analysis, the spectral analysis of a signal, and exploit the fact that we actually expect it to be tuned in ways that every doubling, it becomes kind of the same note. So The chromogram tries to capture this idea of invariance, that the same pitch or the same note played an octave above will have, height perception, which is going to change. So you hear that the same note is higher, but kind of the note itself is the same. So you can have a C here, you can have a C here. All these gray ones are marked as C, and whatever number is here will be, 1, 2, C1, C2, C3, C4, C5, C6. So the numbers are the numbers of the octaves. So these will be the heights, but the notes themselves, these 12, the 8 white ones and the 5, it's 7 plus 5, the 8 is the repetition. So so these 7 plus 5, the 12 notes that you have within each repetition are here. They're represented as, C, C sharp, D, D sharp, E, F, F sharp. So if you count them, you'll get your 12 notes here. So this kind of invariance, or this, in color, people also use three-dimensional representations of combinations of basic colors or other perceptual representations. So you can think about this as sort of that kind of perceptual, graphical or geometrical representation that kind of captures this invariance. We might talk separately about what note is being played and what octave it's being played. So what it means is basically that if we think about the frequency as 2 to the power of some number that goes between 0 and 1, which relates to the chroma here, relates to the actual pitches, okay? And then the h, which are integer numbers, which represent the octaves. So basically we can kind of think about this relation, and then all we do is basically we remove here the octave number and we get the chroma. Check out the math. Basically that's what it is. It takes every frequency at doubling intervals, and what we want now is to say, well, actually we care about all of these intervals, and we will sum them up into an aggregate energy. Same thing we'll do about the next note and next note. So basically kind of wrap all these octaves. We take all the energies in each range of frequencies that corresponds to an octave, and then we add all the energies from the next octave. We add all the energies from the following octave. So we kind of, in this kind of circular way, we sum all the energies, all the frequency analysis energies, and we get an overall energy per chroma or per note without the octave. And this representation, in some sense, captures or summarizes the equivalence, this doubling frequency octave equivalence, and it is very powerful as a way to capture, let's say, chords or collections of notes, because we don't know what partials. So these are chords. These are notations of chords. You're not expected to know what they are, but for those who are musicians, and especially if you kind of play jazz and have seen like lead sheet music, you would have these chords on a guitar. You would learn what they are, basically how you put together notes to have these chords. Now, we don't know what frequencies each of these notes means because of their partial structure. So we try not to remove it. We basically add this, we do this invariant, we summarize all the energies, and then once we get all these energies, we kind of collapse the chord into 12 notes. So what you have here, you have 12 bins, and these 12 bins show, and this is color coding, the red ones would be the stronger overall energies that correspond to this kind of octave relation. And once you do this, you have a good notion of kind of what is the harmony, or what is the combination, what are the chords being played. Of course, you still need to learn and do the mapping here, but you can see that a chord which is a D, okay, chord which is a D, D minor in this case, and I'm sorry that I'm getting maybe a little bit more musically technical, has comprises of notes which are D, F, and A. So D, F, and A, if we look at this Chroma representation, you will have um, an energy at D, an energy at F, and an energy at A. Okay, in this case, white is strong. Okay, let's take whatever the G chord, the G7. It will have G, and then we have B, and we have D, and we should have also an F because it's in 7. If you look up at the peaks, you basically find kind of the equivalent notes that are the strongest. It doesn't mean that there are no other energies in other that correspond to frequencies of other notes, but these are kind of the basic structures that it could be found from the audio signal. And no matter how complex this chord is, because there's this issue that you can space these notes in a different way. For musicians, it's called voicing. You can have the same chord voiced differently, but it will still have this basic structure of which pitches are there, and you can look into that and create this structure. So what chromogram does is basically sums together frequency. And I'll move to next representation, which is called Mel-frequency, MFCC. We won't go too much into the mathematics of what is Capstone coefficient, but I want you to be aware of the Mel scale. So we mentioned that the frequencies that we hear, or the pitches that we hear, are not spaced linearly. When we do the Fourier analysis, we usually have a linear representation, but when we listen or hear the frequencies, they space up in a logarithmic way. Actually, Mel scale tells us what is the way the pitch versus the frequency, how they're related. Okay, so this is more like our sensitivity to different notes, because we perceive pitch actually only in the lower portion of the frequencies. Anything above in 2000 hertz and so on is actually perceived as color, and we cannot actually identify the actual frequency, the actual pitch. We don't have notes above the highest note on the keyboard. But this is kind of the spacing of how we perceive pitch versus how the frequencies, the physical frequencies, behave. So once we have this relation, this is kind of a psychoacoustic study that comes up with these graphs, we can now create this kind of filter. So every triangle here represents some kind of a filter. Think about this as some way of isolating just the frequencies in this band and letting only this aspect of the frequency go through. So you create this bunch of filters that summarize the energies in these frequency bands, and this becomes our Mel scale filter bank. So once we use this Mel frequency scale, then we can take 13 filters from this spacing. Now they will be spaced linear according to the Mel scale. And what we do is we take our signal, we do our Mel filtering, okay? And sorry, I skipped the slide. This is just the way to kind of stretch the Fourier frequency representation in ways that are more psychoacoustically correct. And then there is this Capstone coefficient trick. Now, we can devote a whole class to this. At this point, all I want you to know is that it exists because some of the libraries that we're going to use implement this, and this is a very powerful feature. So, not to devote too much time about this, what is Capstone coefficient? Capstone processing, sometimes called homomorphic processing, is an interesting trick that tries to separate the frequency contents into slow and fast frequencies. It doesn't mean much unless you already heard this term, but this is the mathematical operation that it does, and we'll go back to this idea of how frequencies are represented once we start talking about filters. But MFCC as a feature, basically that's what it does. It takes your signal, he does frequency analysis by doing Fourier analysis, which we also didn't cover in detail, but I think we get kind of the picture what is Fourier. It's this frequency decomposition. Then we spread this into a nonlinear scale, or this kind of a spacing of frequencies. And then we do this trick. We take a log, and then we take another frequency representation. In this case, it's discrete cosine transform, and this ends up being MFCC. Why it's an MFCC? Why this is the correct way? Is this the correct way to kind of understand what what we perceive? Why we do the MFCCs? It's a little bit of a tricky discussion why these features became so popular, why we actually use them to compare sounds, to represent sounds, why we're not happy with the frequency analysis that was done here before, or just spacing them in a Mel scale, which is maybe perceptual. Why do we do this trick? So the idea is that after you do this trick, you kind of separate the idea of pitch also from the overall timbre, and we'll have to show why it happens, and we won't do this today. But there is another justification, which is kind of interesting in the sense that you can think about MFCC as doing two things. I mean, we said perceptual Mel frequency scale, but then if you look at what are the basic frequencies that Mel kind of captures, what are the basic waveforms, we can see that when we will talk about principal component analysis is actually a statistical way to take your data and try to represent this by some templates, some waveforms. So if we usually think about frequencies as our basic templates, so this will be our frequency analysis using sine waves. If we go through the MFCC and we think about them as our waveforms, we can see that they actually start matching so-called principal components, which is an optimal transform. So for those who have heard about PCA, this slide makes sense. For those who did not, just remember that we'll go back to this. But the idea, and that's kind of an empirical finding, that a lot of musical notes, if you try to decompose them in terms of energy using this principal component analysis, and you look at the principal components, you will find that basically MFCC shapes are capturing most of the energy. This is how the PCA works. It actually finds waveforms or templates that capture most of the variance, most of the energy in statistical sense in your data. So if we take a lot of music and we analyze the distribution of energies, we end up finding waveforms which are approximately same waveforms that the MFCC calculates. This is from actually somehow not a very celebrated paper. It was a conference paper, but I found this very interesting because I've never seen this type of interpretation of FCC. Many times, you can go and explain the math, and I think it will make sense what it tries to do. But perceptually, I find this very revealing that MFCC in some sense summarizes in some kind of a perceptually or statistically optimal way the distribution of energies in musical signals. With all this introduction, or I think we're pretty much almost running out of time, what we have here, okay? We'll be using one of the libraries called Librosa, and there is also a paper that is in the repository that kind of explains this toolkit. It's documented also on the web very well, but this is a picture from that paper. And basically what we have here is an example of different types of analysis. And if you want to call them features, yes, I mean, they are features in the sense that, you take your data, you summarize, and you extract some other representation from it. they're human engineered, or these are not learned features. We'll talk, and I mentioned that part of the idea of machine learning today, deep neural network, is that you will actually want to find your own representations. And what I mentioned before about Chroma, not Chroma, the MFCCs, that they are in some sense statistically optimal, but they were not designed this way. So if we take a signal, the first and the most straightforward thing that you will do is analyze its frequency. So this is a linear scale here, and you have short time Fourier transform, and this is basically your standard spectrogram. If you do Mel spectrum, okay, you get slightly different representation. This is not Capstrom, this is Mel spectrum. It's just the spacing, the way it's done is recalculated in ways that corresponds to the Mel scale. This is the chromogram. This basically wraps everything into these 12 bins with, the legend here. The y-axis are actual notes. And then there is something else called the tonnetz. Now, what is tonnetz? This is yet another representation based on musical theory. And I think if you're not too tired from hearing about music theory, that'll be kind of our almost last dive into musical theory aspects. So this is another representation of music that exploits some other very specific ideas about relations between notes and chords. So bear with me for a moment when I explain what tonnetz is. In music theory, many times we use something which is called the circle of fifth. So instead of arranging the notes going by semitones, going from C to C sharp to D like we saw before, we actually rearrange them in jumps of 5, and then we wrap them back. There are a lot of musical theory reasons for doing this. Basically, one of the reasons is that if you go from C to G, which is called the fifth, or 7 semitones up, these would be two notes which are most consonant, and consonant means that they sound together very pleasant. And you can explain consonants, at least to the first approximation, as an idea that they're partial, they're harmonic constituents, these overtones will maximally overlap. And as we said, if we have octave relations, we won't even be able to distinguish between two sounds. If we have a fifth relation, we'll hear them, but since a lot of their harmonics will blend, they will basically fall on the same frequencies. Apparently, it gives us a more of a pleasant feeling. Notes that have a lot of partials that do not overlap, especially if they're close ones, create the sensations of beating, or something that is called roughness. If the beating, like two sinusoids which are close, they're perceived as basically very quickly modulated tone, and it's really an unpleasant feeling. So if you study psychoacoustics, you might encounter this notion of roughness. So there are ways kind of to try to explain why, let's say, two notes playing a fifth apart sound good. But the circle of fifths was actually constructed without even having the psychoacoustical explanation. That's kind of the musical practice. You arrange notes by going, and you loop yourself back by going 7 steps. If you go another 7 steps, you get 14, but then modulo 12, you get 2. You add another 7, you get 9. You get another 7, modulo 2, you get to 4. So basically, this is just rearranging the 12 notes in the relation of fifth. Another consonant relation, or very common relation, especially chords, is that you arrange notes with a distance of minor thirds or major thirds. Again, you have to look it up on the keyboard. Minor thirds, you will go, let's say, from C to the black note, which is, let's say, E flat. So you go C, then go C sharp, D, and then you go E flat. So these are 4 semitones apart. So you kind of aggregate, you take these minor thirds to 0, the 4 and 8, and you kind of aggregate them together. The 3, 7, 11, you aggregate them together, and you get this representation. Major thirds, it's going from C to E. So you'll have actually, let me see, sorry, so this is 0, 3, 6, and 9. This will be 0 and go here, 4 and 11 and 5. Sorry, let me kind of correct myself in terms of the minor and major thirds. So you have basically 3. If you go and you jump minor thirds, you get 4 notes before it wraps together. So you go from 0 to 3 to 3 to 6, 6 to 9. Or if you start from the next one will be from 4 to 7 and so on, you get 3 major thirds. So if you kind of summarize the note, or you arrange the notes in these shapes, okay, now once you have a chord, okay, or you have some relation between notes, you actually take the chromogram that we had before, okay, and you try to represent this as points which are between these notes. Okay, so if you have some kind of chromogram shape, okay, you take the 12-beam tuned chromogram, which kind of represents these so-called pitch classes. So the 12 notes, if you don't have the octave, they're called pitch class. Then you do this transform. So you have these 6 numbers. Every note will be basically represented by 2 coordinates here, 2 coordinates here, and 2 coordinates here. So if you go through this analysis, and I put the whole paper, I put the paper, and so the whole explanation is also in the references. You take your chromogram from 12 notes, you switch this to these 6 coordinates. The first 2 will be how a note is spaced in the circle of fifth, how a note is spaced in the circle of thirds, and minor thirds and major thirds. So once you have that, you end up having these 6 numbers here, okay? And apparently this representation also captures relations between chords and notes. This is actually relations now not between notes, between chords. So if you have an A major chord, you will represent this, you can kind of need to go slowly through the whole derivation to find out why the chord will be actually given as a position in this space, okay, just because it has notes that are part of this chord, so they sum up to these points, and once you kind of have this weighted average, you will basically see that this chord can be represented instead of 1 point in this 12-dimensional chroma, or basically, sorry, a chord will be, you know, a lot of bins in the chroma space. You translate this using this matrix into a 6-dimensional vector, and distances between these vectors are considered much more suitable to comparing distances between chords. So again, a lot of music theory here, and this is why I'm kind of a little hesitant of trying to go too deep into really justifying why it works. Not why, what is the musical reasoning behind this, that kind of relates to these fifth, minor, and major thirds representations. I mean, there is this musical representation which is called the torus, that tries to put chords as points in this three-dimensional space by having these 2 coordinates for each one of the dimensions. But the idea is that once you have this representation, you can start calculating distances. So similar chords in this tonnetz space will be closer, and distant chords in the tonnetz space will be far away. So I think at this point that's the best explanation I can give without taking too much time from our kind of material into really diving into musical theories. You can look up what is tonnetz representation. It's basically a theory of trying to explain the structures of the chords that appear in Western music, or basically music that is based on, you know, the usual kind of octave and chords, major, minor, and diminished, augmented chords that you see in Western music, and very much like the Chroma that tries to wrap up the spectrum into 12 notes. Tonnetz like wants to take multiple pitches which are organized as chords and find another representation that now the distance will be between chords and not between notes. I think that's kind of the best summary I can give, just in terms of thinking about them as features in some musical data space. You know, so kind of repeat, you know, the short time Fourier transform, something scaled according to our perception, Mel scale, pitch class, which is the Chroma. You have the tonnetz, which is really designed for detecting chords, and also MFCC that I don't have right now a graph, but Librosa has it. So I think that pretty much concludes, yeah, that concludes that set of slides. So I'll pause the recording and answer some questions.